Our galaxy is not the boundary of where we belong. It is only a speck carried inside a far greater structure. A continent of galaxies bound together by gravity's invisible pull. That structure has a name whispered across modern cosmology: Laniakea Immeasurable Heaven. And once you see it, the meaning of home changes forever. Laniakea is so vast that even the Milky Way becomes insignificant inside it. It stretches across hundreds of millions of light years, gathering more than 100,000 galaxies into a single flowing system. And we are drifting through it, carried by currents of gravity we cannot feel, yet cannot escape. This story begins at the edge of familiarity, where the idea of our galaxy ends and the truth of our real cosmic address reveals itself. Beyond the stars, we know a larger home is waiting. We often picture the Milky Way as a complete world, a self-contained island where every star, every nebula, every dream of life must reside. But even this majestic spiral is only the first step outward. Our true journey begins by placing the Milky Way into its immediate neighbourhood, the local group. It holds a few dozen galaxies, from the bright sweep of Andromeda to tiny dwarf companions drifting like quiet embers. Together they orbit in a slow gravitational dance bound across millions of years. Yet even this structure, impressive as it seems, is far too small to define our cosmic address. The local group itself is suspended within a broader feature called the local sheet, a thin flattened region where galaxies share similar motions, tilting together through space-time as if shaped by an unseen hand. These layers of structure reveal a pattern. The farther we look, the more the idea of a single home galaxy dissolves. The Milky Way is not a fortress with fixed boundaries, but a passenger within larger and larger systems. And as we take this step beyond familiar stars, we begin to feel the scale pulling away from our assumptions, a hint that the map of our true home stretches far beyond anything we once imagined. The deeper astronomers mapped the local volume, the more they realized something unsettling. Our galaxy's motion could not be explained by the gravity of nearby systems alone. Even when accounting for the pull of Andromeda and the mass of the local group, there remained a residual drift, a steady acceleration tugging us toward a region hidden behind the dense dust of the Milky Way's plane. This invisible pull was first noticed in the 1980s, a quiet oddity in the data that refused to disappear. Galaxies across tens of millions of light-years all seem to lean the same way, as if responding to a distant, overwhelming presence. Scientists called this mysterious influence the Great Attractor, a name that captured both its gravity and its enigma. No one could see it clearly, yet everything nearby moved toward it. For decades, it was a puzzle wrapped in shadows, a gravitational whisper from beyond our line of sight. And with each new measurement, it became harder to deny. The Milky Way is not drifting aimlessly through space, but falling slowly, steadily towards something vast and concealed. The question was no longer whether the Great Attractor existed, but what unimaginable structure could create a pull strong enough to steer entire galaxies. To understand the Great Attractor, astronomers needed a clearer view of the sky. But the universe had placed a barrier directly in their path. The region we needed to study lies behind thick lanes of gas and dust in the Milky Way, a zone so obscured that traditional telescopes see almost nothing. This hidden band is called the Zone of Avoidance, a blind spot carved into our cosmic maps. For decades, it kept the heart of the Great Attractor veiled, leaving scientists to rely on indirect clues. Distorted galaxy velocities, unexpected clustering, and subtle deviations in the cosmic expansion around us. Piece by piece, the evidence lined up. Even without seeing it, astronomers could trace its pull, like watching waves reveal the shape of an unseen island. The Milky Way is one of millions of galaxies drifting toward this shrouded region at enormous speed, a quiet, unstoppable motion written into the fabric of space. And yet, as the picture sharpened, a deeper realization emerged. The Great Attractor was not the final answer. It was only one part of something larger, a gravitational basin embedded inside an even more immense structure. We were not approaching a single object, but the center of a vast interconnected flow. For years, the Great Attractor was treated like a destination, a massive anomaly pulling our galaxy across space. But as astronomers gathered more precise velocity maps, a surprising pattern emerged. Galaxies were not falling straight toward a single point. Instead, their motions curved and branched, flowing along broad gravitational valleys carved into the cosmic landscape. These weren't the paths of objects plunging toward a lone monster of mass. They resembled streams converging into a watershed, each one guided by the contours of something far larger than any cluster we had seen before. This insight changed everything. The universe was not defined by isolated attractors, but by basins of attraction regions where gravity shaped the flow of galaxies across hundreds of millions of light years. The Great Attractor was merely one node inside a wider gravitational domain. And if galaxies all around us were drifting along the same sloping terrain, then we were not witnessing a local anomaly. We were glimpsing the edge of an enormous structure. The question sharpened: what vast shape could guide the motion of so many galaxies at once? And what does it mean for our place inside it? The breakthrough came in 2014 when a team led by Tully at the University of Hawaii attempted something bold. Instead of mapping where galaxies were, they mapped how they moved. By measuring tiny deviations in each galaxy's velocity, motions not caused by cosmic expansion but by gravity, they created a dynamic portrait of our region of the universe. When these velocity vectors were stitched together, a remarkable image appeared. Galaxies across an immense region all flowed toward the same gravitational basin, curving along shared pathways like rivers tracing the shape of an unseen continent. This was no abstract pattern. It was the signature of a giant structure binding them together. The team gave it a name drawn from the Hawaiian language, Laniakea Immeasurable Heaven. Suddenly the Great Attractor made sense. It was merely the central lowland within this vast basin. What we had mistaken for a single gravitational anomaly was only one feature inside a supercluster so large that our entire Milky Way becomes just one fleck carried along its sweeping currents. In that moment, our map of the universe changed, revealing the true scale of the place we call home. To grasp the scale of Laniakea is to confront a size that stretches beyond instinct language or any sense of familiarity. This supercluster spans nearly a region so vast that light itself, the fastest thing in the universe, would need 500 million years just to cross it. Within this expanse lie more than Multimessenger, each containing billions of stars, each star surrounded by worlds we will never see. Our Milky Way, magnificent as it seems from the inside, becomes almost trivial here. A single spark drifting in a continental sweep of galactic islands. Laniakea does not hold these galaxies by walls or borders. It gathers them through motion. Every galaxy inside it participates in a shared gravitational descent toward its center, as if sliding down the same gentle slope of space-time. This collective flow is what defines the supercluster. Not shape, not brightness, but motion itself. And once you see the Milky Way as part of this ocean of galaxies, the idea of where we live expands into something quiet, humbling and impossibly grand. A home measured not in stars, but in the currents that carry them. Unlike the neat circles and spirals we draw in textbooks, Laniakea has no simple outline. It is not a cluster with a clear edge nor a sphere bound by gravity in the usual sense. Its borders are defined by motion, the places where galaxies stop flowing toward the same gravitational basin and begin drifting toward another. Imagine a vast landscape of invisible slopes carved into space-time. Every galaxy inside Laniakea slides gently downhill toward the region we call the Great Attractor. Just beyond that boundary, the slope tilts a different way, pulling galaxies toward neighbouring giants like the Perseus-Pisces supercluster or the Shapley concentration. These changes in flow create the true perimeter of Laniakea, a shifting frontier drawn by the direction of motion, not by light or mass. It is a boundary you cannot see, yet one every galaxy obeys. This way of defining a supercluster reveals a universe shaped less like a collection of islands and more like a network of river basins, each one channeling galaxies along pathways that stretch across hundreds of millions of light years. And now that we can trace these currents, a new question rises. What lies at the heart of this immense gravitational valley? At the center of Laniakea's vast gravitational basin lies the region that first betrayed its presence, the Great Attractor. But seen now through the lens of the supercluster, it is not a cosmic monster swallowing galaxies. It is the lowest point in an immense valley of space-time, a gravitational hollow where countless flows converge. This convergence isn't sudden or violent. It is slow, steady, and ancient, guiding galaxies over hundreds of millions of years. Inside this region sits the Norma cluster, a dense concentration of galaxies hidden behind the Milky Way's dust, massive enough to bend the trajectories of whole galactic families. Its gravity creates the downward slope that draws the Milky Way Andromeda and thousands of others toward the same unseen center. Yet even here at the floor of the basin we find no final answer, only a deeper mystery. The Great Attractor is powerful but not alone. Its influence is intertwined with other colossal structures beyond it, hinting that even Laniakea's heart is part of a larger story. As we peer into this hidden center, the universe feels less like a map with borders and more like a web of forces, each shaping the paths of galaxies across unimaginable distances. As astronomers push their maps beyond the heart of Laniakea, they discover that our supercluster does not exist in isolation. Its flows, though coherent and graceful, brush against the edges of even larger gravitational realms. Just beyond our boundaries lies the immense Shapley concentration, a titanic assembly of galaxy clusters whose mass dwarfs anything within Laniakea. Its gravitational pull stretches across hundreds of millions of light years, subtly tugging on our entire region and tilting the cosmic landscape in its direction. Farther still, another giant, the Perseus-Pisces supercluster, shapes the motion of galaxies along one of the longest filaments ever observed. These surrounding structures do not disrupt Laniakea, they frame it. Their combined gravity defines the ridgelines where our flows end, and theirs begin like mountain ranges separating colossal river systems. In this larger map, Laniakea becomes one watershed among many, part of a sprawling web of basins and valleys carved by dark matter across the universe. And as these connections come into focus, a profound truth emerges. To understand our home, we must see not just our own supercluster, but the vast network that holds all of them together. When we zoom out far enough to escape the confines of any single supercluster, the universe reveals its true architecture, a vast cosmic web woven from filaments of dark matter and chains of galaxies stretching across billions of light years. In this view, Laniakea is not a lone titan, but a single shimmering branch in an immense network, one thread among countless others that lace the cosmos together. These filaments act like highways of gravity, guiding galaxies along predetermined paths carved in the earliest moments after the Big Bang. Between them lie enormous voids, regions so empty that entire clusters drift along their edges without ever crossing inside. The cosmic web is not a metaphor. It is the actual shape of matter on the grandest scales, a scaffold where light and gravity follow patterns written long before stars first burned. And somewhere within this web our supercluster hangs like a delicate drop of light suspended in the dark framework that holds the universe together. To understand Laniakea, we must see it as part of this larger tapestry, a single note in a cosmic composition whose scale defies imagination. Amid the vast filaments and drifting basins of the cosmic web, the Milky Way occupies a place so small it barely registers on the grand map, yet its position is anything but random. Our galaxy resides on a minor branch of Laniakea known as the Orion Spur, a modest lane of stars rising from one of the Milky Way's outer arms. From here, we join Andromeda Triangulum and dozens of dwarf galaxies within the local group, all sharing the same gentle descent toward the Great Attractor. This entire assembly moves together like a cluster of leaves carried by the same distant current. The structure around us. The local sheet tilts our motion even further, aligning our path with thousands of other galaxies spread across the supercluster. When viewed from afar, the Milky Way becomes just one luminous droplet sliding along Laniakea's gravitational slope, insignificant in size yet perfectly embedded in a coherent, elegant flow. Our position is not at the centre nor at any special crossroads. Instead, we occupy a quiet, stable corner of a structure so immense that only now are we learning to trace its shape. And in understanding where the Milky Way fits, we begin to understand where we fit. If Laniakea is the landscape, then dark matter is its hidden bedrock, the invisible framework shaping every valley, ridge and river of galaxies. Though it emits no light and reveals no surface, its gravity sculpts the motion of everything within the supercluster. Astronomers can trace its presence only through effects. The way galaxies orbit too fast to be held together by visible matter alone, the way their paths curve gently toward mass. We cannot see the way entire clusters align along unseen threads. In Laniakea, dark matter forms the deep gravitational channels that guide our drift toward the Great Attractor. Without it, the supercluster would dissolve its galaxies, scattering into the expanding universe. Instead, they remain tied to a vast silent architecture older than any star. Even the Milky Way's path, our slow descent across tens of millions of light years, is dictated by this invisible scaffold. We are passengers on a structure we cannot touch, yet one that defines every motion we make. And once we recognize that dark matter holds the blueprint of Laniakea, one question becomes impossible to ignore. How did such a colossal form ever emerge from the early universe? The origins of Laniakea reach back to a time long before galaxies existed, when the universe was a hot, dense fog of particles only minutes after the Big Bang. In the early chaos, tiny fluctuations in density, mere ripples in the cosmic fire, determined where matter would later gather. Regions with slightly more mass pulled harder on their surroundings, growing into vast wells that deepened over millions of years. Dark matter, cooling faster than ordinary matter, fell into these wells first, forming an intricate skeleton of invisible filaments. As the universe expanded and cooled, ordinary matter followed this framework, settling into the densest knots, where the first galaxies ignited. Over billions of years, these knots merged, linked and stretched into the colossal superstructures we see today. Laniakea is one of them, the end result of a gravitational story written into the universe from its very first seconds. Every flow of galaxies, every gentle slope of space-time can be traced back to those ancient ripples frozen into the cosmic background. And as we uncover this origin, it becomes clear that our supercluster is not just a place in space, but a fossil of the universe's earliest patterns. As the universe aged, the early seeds of structure began to stretch into recognizable forms. Gravity gathered galaxies into clusters. Clusters merged into chains, and those chains thickened into the sprawling filaments that shape Laniakea today. Yet this evolution was anything but smooth. Collisions between galaxy groups sent shockwaves of star formation through the young supercluster, lighting its filaments like cosmic embers. Meanwhile, dark matter continued to tighten its grip, deepening the gravitational valleys that directed every motion within the basin. Over billions of years, these flows became more coherent, guiding galaxies along steady, predictable paths toward the region we now call the Great Attractor. Even the Milky Way's own history, its growth, its mergers, its current trajectory was sculpted by this unfolding architecture. Laniakea did not simply form and settle. It matured, pulsing with the movement of matter across unimaginable distances. And as its structure sharpened, one quiet truth emerged. Superclusters are not permanent. They are moments in the universe's long story, shaped by gravity now, but destined to be transformed by cosmic expansion. The question is no longer how Laniakea formed, but how it will change in the ages to come. As the universe continues to expand, the fate of Laniakea is shaped by a quiet tension between gravity and dark energy. Gravity binds the galaxies within the supercluster, drawing them steadily toward its center, but dark energy pushes the fabric of space apart with relentless persistence. Over the next billions of years, this tug-of-war will sculpt Laniakea's future. Galaxies already drifting toward the Great Attractor will continue their descent, merging into ever denser clusters as their motions fall deeper into the gravitational basin. Meanwhile, the outer edges of Laniakea will begin to fray. Expansion accelerates the space between superclusters, stretching the cosmic web until its largest filaments thin and detach. Beyond a certain distance, galaxies will no longer be able to reach one another. The expansion will outrun gravity's pull. Laniakea will persevere as a single island of matter, but everything outside it will drift beyond visibility, carried away by a universe that grows faster than light can cross. In time, our supercluster will stand alone in a deepening cosmic darkness, a final sanctuary of galaxies bound together while the rest of the universe slips beyond reach. Within this future, the Milky Way and its closest companions follow a path already set in motion. Long before the expansion isolates Laniakea from the wider universe, our own local group will undergo its most dramatic transformation. The Milky Way and Andromeda, drawn together by mutual gravity, are on course to collide in about 4 billion years. This encounter will not be an explosive crash, but a slow, majestic merging their stars, passing through one another like ghosts, while tidal forces reshape both galaxies. Over time, their spiral arms will stretch, twist and fade, settling into a single giant elliptical system, often called Milkdromeda. This newly formed galaxy will drift deeper into Laniakea's gravitational basin, continuing the descent that began long before the Sun was born. Smaller galaxies, Triangulum and the many dwarfs orbiting us, will eventually join this merger, adding their stars to the growing core. In the far future, our corner of Laniakea will become quieter, simpler, and dominated by this immense merged remnant. And as Milkdromeda journeys onward, it carries with it the story of every star that once belonged to our galactic family. Far beyond the future of any single galaxy, the destiny of the entire Laniakea Supercluster unfolds on scales almost impossible to imagine. As dark energy accelerates the expansion of the universe, the great filaments connecting Laniakea to neighbouring structures will stretch thinner and eventually snap, leaving our supercluster drifting alone in a widening gulf of emptiness. Within its boundaries, gravity will continue to sculpt the remaining clusters, drawing them inward as the outer regions grow quieter and more isolated. Over trillions of years, star formation will fade as gas is consumed or expelled, and the bright spirals that once filled Laniakea will settle into ancient reddish remnants. The cosmic web around us will dim its patterns, softened by time, until only the densest cores remain visible. Yet even in this distant future, Laniakea endures as a single gravitational island, a final oasis of matter in a universe where expansion has swallowed nearly everything else. In this grand silence, the supercluster becomes a monument to what the cosmos once was. Dynamic, interconnected, and filled with rivers of galaxies flowing across unimaginable distances. As Laniakea moves toward its distant, quiet future, a deeper perspective begins to emerge, one that reshapes how we think about home in the vastness of space. From the scale of planets and stars, the Milky Way feels enormous, an entire island of light containing our history, our stories, and every trace of life we know. But when placed inside Laniakea, it becomes clear that our galaxy is only a single eddy in a far larger flow carried along pathways carved long before life existed on Earth. Even our local group, with all its galaxies intertwined, is just one small tributary, feeding into the supercluster's immense gravitational basin. This realization is not meant to diminish our place in the universe, but to expand it. We do not live in isolation. We inhabit a structure so large and intricate that it cannot be seen in a single glance, or even a single lifetime of study. Laniakea is the broader stage in which every chapter of cosmic evolution around us has unfolded, and understanding this context does something profound. It reveals that our true home is not just one galaxy, but an entire region of space woven together by gravity, motion, and time. For most of human history, the idea of a supercluster would have been unthinkable. Ancient astronomers saw the night sky as a fixed dome, a tranquil stage where stars drifted slowly but never truly changed. Even after telescopes revealed nebulae and distant galaxies, our cosmic picture remained small. We believed the Milky Way was the whole of creation, a lone island adrift in darkness. Only in the last century did our understanding begin to widen, first with the discovery that other galaxies existed, then with the realization that they formed clusters, and finally with the shocking truth that even those clusters were merely fragments of larger structures. Laniakea represents the culmination of that journey, the latest step in a long chain of revelations carved by light and mathematics. It reminds us that our perception of the universe has always expanded, never contracted, each discovery forcing us to redraw the borders of the known. What once seemed immense now fits inside something larger, and what we see today will someday be only a chapter in an even greater map. The story of Laniakea is in many ways the story of how humanity learned to see. The ability to uncover Laniakea did not come from a single telescope, but from a new way of listening to the universe. Instead of mapping galaxies by where they appear in the sky, astronomers began to track how they move, the subtle deviations in their speed and direction that reveal the hidden pull of gravity. These peculiar velocities, tiny shifts buried beneath the overwhelming expansion of the cosmos, allowed scientists to trace the invisible slopes guiding whole clusters across space. It was like watching fallen leaves drift on a river and using their motions to reconstruct the shape of the water beneath. Radio surveys pierced regions hidden by the Milky Way's dust infrared observations, mapped galaxies long obscured from view, and supercomputers stitched millions of data points into a coherent three-dimensional flow. For the first time, we could see not just the locations of galaxies but the paths they followed. And those paths all curved toward the same immense basin, a signature written unmistakably across the cosmic landscape. Without these modern tools, Laniakea would have remained invisible, its structure too vast and too subtle to grasp. With them, the universe revealed a truth it had kept hidden for billions of years. What makes Laniakea truly astonishing is not just its size, but the graceful coherence of its motion. When astronomers traced the peculiar velocities of thousands of galaxies, a pattern emerged that was impossible to ignore. Every galaxy within this vast region flowed along gently curving paths toward the same gravitational basin. These were not chaotic trajectories or random drifts. They formed organized streams, each following the contours of dark matter beneath them, like rivers seeking the lowest valley. In some areas, the flows merged into broad channels. In others, they parted around massive clusters before converging again farther downstream. This choreography revealed a truth deeper than any map of galaxy positions could show. Laniakea is not defined by where galaxies are, but by how they move together. Their shared descent gives the supercluster its identity, uniting more than 100,000 galaxies into a single dynamic structure. And as this vast pattern came into focus, it transformed our understanding of the cosmos. The universe is not a static scattering of islands. It is a landscape shaped by tides of gravity, where every galaxy carries the imprint of ancient forces sculpting its path across millions of light years. This shared motion also reveals something profound about the connections between galaxies. Even though they are separated by millions of light years, they are not isolated wanderers drifting through an empty void. Each one is tied to countless others through the subtle pull of gravity woven across the cosmic web. A galaxy on one side of Laniakea can influence and be influenced by galaxies far beyond its luminous reach, because all of them respond to the same underlying architecture of dark matter. In this sense, Laniakea behaves like a single organism composed of many parts, clusters acting as organs, filaments as arteries and flows, as the lifeblood moving through its vast frame. The Milky Way's journey toward the great Attractor is only one thread in this immense tapestry, intertwined with thousands of parallel paths tracing the same gravitational valley. What appears from Earth as a quiet night sky is on the scale of the supercluster, a coordinated migration of galaxies shaped by forces older than any star. An understanding that connection transforms our view of the cosmos. Every galaxy is part of a larger motion, and every motion reveals the invisible structure holding the universe together. Within this vast network, the Milky Way plays a quieter role than many imagine. It is neither a dominant cluster nor a major hub, but a modest participant woven into one of Laniakea's countless streams. Our galaxy drifts along the gravitational slope with no control over its path, carried by the same ancient forces steering thousands of others. And yet this very ordinariness is what makes our position remarkable. From our tiny corner on the Orion spur, humanity has managed to trace the supercluster's structure, measure its flows and map its hidden architecture. We look outward from a galaxy that is unexceptional in mass shape and influence, yet we're able to comprehend the colossal system moving us through space. The Milky Way is a passenger, but we are the observers riding within it, the only known beings capable of recognizing the pattern guiding our motion. This perspective reframes our place in Laniakea. We are not central, but we are aware. Not significant by size, but extraordinary by understanding. And as our instruments grow more precise, the map of our supercluster becomes sharper, preparing us for an even deeper revelation about the forces shaping our journey. As our map of Laniakea sharpens, a new layer of complexity emerges. The supercluster is not a rigid structure, but a living pattern shaped by motion itself. Every galaxy inside it, including the Milky Way, follows a trajectory influenced by countless gravitational nudges from clusters, filaments, and dark matter streams. These influences change slowly over cosmic time, creating flows that twist, stretch, and reorganize as the universe evolves. Laniakea's shape is therefore not fixed, but gently shifting, a colossal pattern drawn in motion, not in stone. And the closer we study these currents, the more clearly we see how deeply they connect us to the wider cosmic landscape. These flows reveal that Laniakea is less a place and more a process, a continual reshaping guided by the slow choreography of gravity across hundreds of millions of light years. The Milky Way carried along one of these immense currents as part of a migration that began before our Sun existed, and will continue long after our galaxy transforms into something new. In tracing these motions, we uncover not just where we are, but how we are moving through the universe. And with that, the supercluster becomes more than a map. It becomes a story still unfolding. The more we follow these vast currents, the more the universe resembles a grand migration rather than a static architecture. Galaxies are not anchored to fixed coordinates. They drift, gather separate, and reshape the contours of their surroundings as they move. Laniakea, seen through this lens, becomes a waypoint in a far longer journey. A chapter in the cosmic motion that has carried matter from the first moments after the Big Bang to the structures we see today. Every flow we map is a fragment of that ancient momentum still unfolding across unimaginable distances. Within this immense drift, the Milky Way's path is both ordinary and profound. It follows the same gravitational slopes as countless neighbouring galaxies, yet from our vantage point we are the first to trace these currents with intention. By observing how everything around us moves, humanity has begun to read the larger story of the cosmos, not just its shapes, but its directions, its tides, its quiet momentum. Laniakea becomes clearer with every measurement, revealing a universe where motion, not location, defines our true place. And this deeper understanding guides us toward the next question. What does this motion mean for our future? As we look ahead, the motions weaving through Laniakea reveal more than a simple drift through space. They hint at the long-term destiny of our cosmic neighbourhood, Every galaxy within the supercluster is slowly descending the same gravitational valley, sliding toward its center in a migration measured not in centuries, but in billions of years. This descent is gentle, almost imperceptible on human timescales, yet relentless across cosmic ones. The Milky Way, Andromeda, and countless others are all participants in this slow convergence, their paths shaped by dark matter channels laid down in the universe's earliest moments. And while this motion will not lead to violent collapse, it will gradually tighten the structure of Laniakea, drawing clusters inward, as the expanding universe stretches everything beyond its borders away. In the far future, these inward flows will become the last visible traces of a universe once rich with interconnected structures. Long after distant superclusters have faded beyond reach, the galaxies of Laniakea will continue their ancient journey, following the contours of a gravitational basin that has guided them since time began. In understanding this motion, we glimpse not only our place in space, but our place in time. As the great currents of Laniakea come into focus, something subtle but profound begins to shift in our understanding. These flows are not just astronomical curiosities, they redefine how we think about our place in the universe. For the first time, humanity can trace the path of its own galaxy, through a structure so vast that it dwarfs every idea of home we once held. We are no longer anchored to a fixed point in space. We are travelers embedded in a slow, majestic motion that began long before Earth formed and will continue long after the last stars fade. This realization challenges the familiar image of the cosmos as a collection of isolated objects. Instead, it reveals a universe shaped by relationships, by the gentle pull between galaxies, by contours carved in dark matter, by the shared descent of countless worlds toward the same gravitational basin. And within that pattern, our existence becomes part of a sweeping, interconnected story. The Milky Way does not drift alone. It moves with purpose written into the fabric of space-time. To understand these flows is to glimpse the larger narrative unfolding around us, one that places our galaxy and our species inside a much grander motion than we ever imagined. As our understanding deepens, the idea of home stretches far beyond anything earlier generations could imagine. Earth once felt like the center of everything. Later the Sun took that role, then the Milky Way, and then the local group. But with Laniakea, the scale changes so dramatically that our old notions fall away. Home is no longer a point on a map. It is a flowing region of space, a gravitational landscape shaped by forces we cannot see yet, can measure with astonishing precision. Within this vast basin, every galaxy takes part in the same gentle descent, as if all of them were threads woven into a single cosmic fabric. The Milky Way is one such thread carrying us through the supercluster, on a journey lasting billions of years, and in seeing this, truly seeing it, we gain a new perspective on belonging. We do not stand apart from the universe. We are part of its motion, its history, its evolving architecture. Laniakea becomes not just the place we occupy, but the structure that holds our past and guides our future. To understand it is to understand the larger story in which our brief moment of existence is written. The more we uncover about Laniakea, the more our perception shifts from seeing the universe as a distant spectacle to recognizing it as an environment we actively inhabit. Our species evolved on a small planet orbiting an ordinary star, yet we have learned to read patterns written across hundreds of millions of light years. This ability to trace flows of galaxies, to map unseen structures, to decode the shapes carved by gravity, connects human curiosity directly to the architecture of the cosmos. It is a reminder that understanding the universe is not merely an academic pursuit. It is a form of orientation, a way of discovering where we truly stand in the vastness around us. In this sense, Laniakea becomes both a scientific revelation and a philosophical anchor. It shows that even in a universe without fixed centers, knowledge can provide its own form of grounding. We may be small, but we are not lost. By charting the supercluster that carries us, we gain a deeper sense of belonging, not to a single world or galaxy, but to a structure so grand that our journey through it becomes part of the cosmic narrative itself. As our view expands, a powerful realization grows alongside it. The universe is not simply something we observe, it is something we move through. Every discovery from the Milky Way's rotation to the flows of Laniakea reveals that we are participants in a cosmic journey unfolding across billions of years. Human understanding becomes a bridge between the incomprehensible scales of the universe and the fragile moment we occupy within it. With each new map, each refined measurement, we align ourselves more closely with the true structure of reality. The expansion of the universe, the descent along gravitational valleys, the formation of superclusters. These are no longer abstract events happening out there. They are the forces shaping the trajectory of our own galaxy, our own star, our own future. In learning this, our perspective subtly shifts. We stop seeing ourselves as spectators at the edge of an indifferent cosmos, and instead recognize that we are entwined with it, woven into its flows and its history. Understanding Laniakea becomes a way of understanding the path ahead, not just for galaxies, but for the fragile spark of awareness traveling with them. As we continue tracing our place within Laniakea, one truth becomes increasingly clear. Knowledge is the tool that anchors us in the universe without fixed boundaries. The cosmos offers no central point, no privileged location from which everything else unfolds. Instead, it presents a shifting landscape of motion, structure, and expansion. Yet through observation and reason, humanity has carved out a sense of orientation that no map could ever provide on its own. By understanding the flows that guide our galaxy, we learn not just where we are, but how we are carried through the deep currents of space-time. This understanding becomes a form of stability in a universe defined by change. The more we uncover about the architecture around us, the filaments, the basins, the gravitational contours, the more clearly we see our own trajectory written into them. Laniakea stops being a distant abstraction and becomes a frame of reference, a coordinate system built not from lines and angles, but from relationships and motion. And with that realization, we begin to grasp something profound. Our future, both as a species and as a civilization, will depend on how deeply we understand the cosmic environment that shapes every moment of our existence. As our understanding of Laniakea deepens, we begin to see how the cosmic environment shapes not only our galaxy's future, but our own potential as a civilization. For humanity, knowledge of these immense structures is more than curiosity, it is preparation. The gravitational flows guiding the Milky Way will influence our long-term cosmic trajectory, just as surely as climate and geography shaped the early paths of human cultures on Earth. If our species endures long enough to explore beyond the boundaries of the Milky Way, these flows will define the routes available to us, the regions we can reach, and the future homes we might one day inhabit. Even on shorter timescales, understanding our place within Laniakea gives context to the fragile moment we occupy. A brief interval when the universe is still richly interconnected before cosmic expansion isolates each supercluster into its own island of matter. Recognizing this fleeting openness imbues our era with a kind of urgency. We live at a time when the universe is still accessible, still readable, and knowing that may shape the choices humanity makes as it steps beyond its birthplace. We live in a remarkable moment, one that occupies a narrow window in the universe's long history. For the first time, humanity has the tools to map structures hundreds of millions of light years across. Yet we do so in an era when those structures are still visible and still connected. Future civilizations born trillions of years from now will not have this privilege. By then, cosmic expansion will have carried every supercluster beyond the horizon of visibility, leaving only the remnants of Laniakea accessible to observers. The wider universe, its filaments, its neighbouring giants, its grand architecture will fade into darkness unreachable and unknowable. But we exist at a frontier of knowledge, a time when the cosmos still reveals its design to those who look deeply enough. This makes our moment not just scientifically rich, but cosmically rare. Our generation holds the ability to understand the true structure of our home, to witness Laniakea in its full splendor before the universe slips into isolation. And recognizing this rarity gives our search meaning. We are not just mapping the universe, we are preserving the last era in which its vastness can be understood. Understanding Laniakea is more than an exercise in cosmic cartography. It is an act of appreciation for the fleeting clarity our era provides. To see the universe as it truly is, with its sprawling filaments and vast river systems of galaxies, is to witness a structure that future observers will never be able to reconstruct. Every map we create, every flow we trace, becomes part of humanity's long-term memory of a cosmos that once revealed itself openly. In this sense, Laniakea is not just a supercluster. It is a monument to the age of transparency. We inhabit a reminder that the universe is offering us its blueprint now, while the lights of distant realms still reach us. And as we come to understand this, our view of the night sky transforms. The Milky Way is no longer a solitary arc of stars, it is one branch of a much larger design. A design we have the privilege to witness precisely because we exist at this moment in time. To comprehend Laniakea is to cherish the rare clarity our generation holds, and to recognize that our curiosity preserves a truth the universe will one day hide. Living within Laniakea gives our existence a quiet, almost poetic context. We are not simply residents of a planet or even a galaxy. We are part of a vast unfolding motion that began long before life emerged on Earth. Every atom in our bodies, every mountain, every ocean has been carried through this supercluster for billions of years, tracing a path carved by forces we only recently learned to measure. This awareness does not make us smaller. It makes our story richer. To know that we drift with 100,000 galaxies along the same graceful descent is to feel connected to something immeasurably larger than ourselves. It turns the night sky from a backdrop into a landscape, a place we belong to, not a scene we simply observe. Laniakea becomes the stage on which our entire history has played out, the gravitational valley that shaped our trajectory long before our species learned to look upward. And as we recognize this, a subtle shift happens within us. The universe stops feeling distant. It becomes personal. It becomes home. Calling Laniakea our real home is not a metaphor. It is a recognition of the true scale that shapes our existence. Home is the environment that guides us, the structure that carries us, the context without which our story cannot be understood. By that definition, Laniakea is as fundamental to our identity as the Milky Way itself. It is the gravitational cradle in which our galaxy formed, evolved, and continues to move. Every star ever born in the Milky Way, including our Sun, has traced its life along the contours of this supercluster. Every civilization that might arise within its boundaries will share the same grand motion, falling together through the same vast valley of space-time. When we understand this, a powerful sense of belonging emerges, not rooted in geography but in motion. We are part of a family of galaxies traveling together through the universe, connected not by proximity but by a shared descent shaped billions of years ago. Laniakea becomes a reminder that our place in the cosmos is not defined by isolation but by connection. In its immense scale, it gathers us into a larger story, one that began before we existed, and will continue long after we're gone. Once we see Laniakea as our true home, the galaxies around us stop being distant curiosities and become something closer to relatives. Andromeda Triangulum, the countless dwarfs scattered through our local group, all of them share the same long descent through the supercluster. Farther out, great clusters and chains of galaxies, many we will never visit, still travel with us along the same gravitational valley. They are part of the same migration, shaped by the same dark matter skeleton, and guided by the same invisible slopes of space-time. Each galaxy traces its own internal history, stars born and dying planets, forming perhaps even life emerging. Yet all of those stories unfold within a shared motion that unites them. In this light, Laniakea becomes more than a backdrop. It is a community of galaxies bound not by communication or culture, but by physics itself. We may never meet whatever worlds exist within those distant spirals, but we already know one thing we share with them: a common journey written in gravity carrying us together through the same immeasurable heaven. When we recognize ourselves as citizens of Laniakea, something shifts in how we think about humanity's place in the cosmos. We stop seeing Earth as an isolated stage and begin to understand it as one world within a vast shared environment. Our story becomes part of a larger narrative written across hundreds of millions of light years, shaped by the same gravitational currents that guide entire clusters. This sense of cosmic citizenship does not make us insignificant. It gives our existence context. Just as ancient explorers once mapped oceans and continents to understand their world, we are now charting the immense structures that cradle our galaxy. And within those structures we find both humility and belonging. We belong to the Milky Way, to the local group, to the Laniakea Supercluster, and through them to the cosmic web that stretches beyond imagination. Understanding this hierarchy of homes reminds us that our roots extend far beyond the Earth beneath our feet. We are shaped by forces older than our planet, carried by a motion wider than our galaxy, and connected to a journey that began before time had meaning. As this broader sense of belonging settles in, our relationship with the universe begins to feel less abstract and more intimate. We are no longer observers peering outward from a single planet, but participants immersed in a structure that influences us on every scale. The same gravity that shapes Laniakea's immense basin also governs the orbit of Earth, the tides of our oceans, and the formation of every star we see. The forces that guide whole clusters move through us as well, connecting the fate of galaxies to the quiet rhythms of our own world. This unity invites a new kind of awareness, one that blends scientific understanding with a deeper appreciation of our place in the cosmos. To live inside Laniakea is to exist within a masterpiece of motion and structure, a living tapestry woven over billions of years. And knowing this enriches the simple act of looking at the night sky. Each point of light becomes part of the environment that shaped us, part of the shared journey we take through the immeasurable heaven. In seeing the universe this way, we do not just learn where we are, we learn who we are within it. The deeper we look, the more the universe reveals a harmony between the smallest scales of existence and the largest structures that surround us. The atoms in our bodies were forged in ancient stars, yet the paths of those stars were shaped by the gravitational contours of Laniakea. The chemistry of life depends on elements born in supernova, but the motion of those stellar ancestors was guided by the same invisible slopes that direct entire galaxies. Even the arc of Earth's orbit traces a pattern ultimately influenced by forces stretching hundreds of millions of light years across. This unity does not diminish the beauty of the small, it elevates it. The warmth of sunlight, the formation of clouds, the growth of forests, all are threads woven into the same tapestry that binds clusters and filaments into a cosmic web. In this sense, the everyday world is a reflection of the universe's deepest architecture. To recognize this is to see that the boundary between the local and the cosmic is thinner than we once believed. We are shaped by Laniakea in ways both grand and intimate, carried through a supercluster whose influence reaches all the way down to the scale of life itself. In a universe where everything is shaped by forces older than time itself, humanity plays a surprisingly vital role. We are the storytellers of the cosmos. Laniakea existed long before our species appeared, and it will continue long after the last traces of our civilization fade. Yet for this brief moment, we are the ones capable of mapping it, naming it, and understanding the immense structure that carries our galaxy through space. Every observation we make becomes part of a record that future generations, or perhaps no one at all, may one day look back on. The universe does not require witnesses, but the act of witnessing transforms our fleeting existence into something enduring. By charting Laniakea's contours, by tracing its cosmic flows, and revealing its hidden architecture, we give meaning to a structure that would otherwise remain silent. In doing so, we bridge the gap between the incomprehensible scale of the supercluster and the fragile consciousness that seeks to understand it. This is humanity's quiet contribution to the cosmos, not to shape it, but to know it. And in knowing it, we become part of its unfolding story. As the universe changes around us, the maps we create become more than scientific achievements. They become safeguards for knowledge that the cosmos itself will eventually erase. The structures we see today, the bridges of galaxies stretching across hundreds of millions of light years, will not remain visible forever. Cosmic expansion will thin the filaments, dim the distant clusters, and finally push whole realms of matter beyond the reach of light. Yet the record we leave behind the charts, the simulations, the measurements of flows and motions, will preserve a picture of a universe more connected and magnificent than any future observer will be able to witness. In this way, our understanding of Laniakea becomes a legacy. It captures a moment of cosmic openness, a snapshot of the grand design before isolation takes hold. And even if humanity changes, migrates, or one day disappears, this knowledge remains a message carved into time itself. A reminder that once in an era when the universe could still be seen in full, a species on a small blue world learned to map its true home among the stars. Through knowledge, we hold on to a universe that is already slipping away. In the vast arc of cosmic time, the legacy we leave is not measured in monuments or empires, but in the clarity with which we understood our place in the universe. Every equation, every star catalogue, every map of Laniakea becomes a testament to a species that refused to remain blind in the dark. We are fragile, brief and small, yet we have learned to read the structure of a supercluster stretching hundreds of millions of light years across. This act alone elevates our existence. It means that for a moment in the history of the cosmos, awareness blossomed inside a galaxy, drifting quietly through Laniakea's gravitational valley. And from that awareness came understanding. If one day humanity travels beyond the Milky Way or transforms into something new or fades entirely, the knowledge we have gathered will still stand as evidence that consciousness once illuminated this corner of the universe. The maps we draw, the truths we uncover are not just scientific records, they are declarations of presence. They say, "We were here and we understood something magnificent." In that understanding, we offer the universe the only gift it cannot create on its own: perspective. Knowledge does not end with our discoveries. It becomes the foundation for everything that follows. Each generation inherits a clearer picture of the universe, extending the reach of those who came before. The first astronomers mapped constellations. Centuries later, we mapped galaxies. Now we map the flows of an entire supercluster. This continuity is what transforms curiosity into progress. Understanding Laniakea is not a final revelation, but a stepping stone, a platform from which future minds will look even farther and question even deeper. Perhaps they will trace structures we cannot yet detect or uncover new forces shaping the cosmic web. Perhaps they will stand on distant worlds gazing at new skies, carrying with them the same desire that pushed us to chart our place in the universe. In this way, our exploration becomes an unbroken thread woven through time, binding our past, present and future to the same pursuit. To know where we are and to understand the vastness that holds us, Laniakea is part of that thread, a chapter in a long story still being written, guiding the next steps of a species determined to keep learning. If humanity's story continues, our curiosity will eventually push us beyond the familiar borders of the Milky Way. Long after our civilization masters the scale of planets and stars, we may begin to think in the natural units of Laniakea itself, clusters, filaments, and the vast currents that bind them. The routes we chart through interstellar space will one day extend into intergalactic pathways, shaped by the same gravitational slopes that guide entire galaxies. Traveling between stars may be only the first chapter of a far longer journey. Even if such voyages unfold over millennia guided by patient generations or forms of intelligence yet to emerge, The direction of travel will already be chosen by the architecture of our supercluster. The flows of Laniakea will become our cosmic highways, subtle but persistent, carrying future explorers along the contours of a superstructure carved at the dawn of time. And as they move outward, they will not be leaving home, they will be moving through it. For in a universe defined by motion, exploration is simply the act of following the path our galaxy has been tracing for billions of years. As we envision this distant future, one idea becomes clear. The universe rewards the minds that dare to understand it. Intelligence, wherever it arises, becomes a way for the cosmos to examine itself. When humanity maps Laniakea, it is not merely gathering data. It is giving the universe a means to know its own shape. And one day, if explorers carry our curiosity into the deeper currents of the supercluster, that act of seeking will become a continuation of the same cosmic introspection. Across centuries or millennia, thought itself may travel along the gravitational pathways that guide galaxies drifting outward as naturally as starlight. Whether humanity evolves, merges with its machines, or becomes something entirely new, the drive to understand will remain the thread connecting each era. In that sense, the long journey through Laniakea is not only physical but intellectual, a migration of awareness expanding into larger and larger frames of meaning. And as long as that curiosity survives, the universe will never be a silent, empty place. It will be a story continually reinterpreted by the minds that rise within it. Even in the far future, as civilizations rise, transform, or fade, Laniakea will continue shaping the canvas on which their stories unfold. The great gravitational basin that guides our galaxy will remain a constant backdrop long after planets shift. Stars evolve or species change form. Its currents will determine which regions of the cosmos remain reachable, which clusters drift closer, and which fade beyond the cosmic horizon. Any intelligence that emerges within this supercluster, whether descended from humanity or born independently in a distant spiral, will inherit the same vast environment shaped by the same invisible architecture. In this way, Laniakea becomes a unifying thread across time, connecting the destinies of countless worlds through shared motion. And even if these civilizations never meet, they will still be companions in the same silent migration, carried together through an ocean of space-time too wide for any single species to cross alone. This enduring framework reminds us that the universe is not only enormous, it is coherent. Its structure holds stories that extend far beyond our own, and in understanding it, we touch the continuity that links every era of cosmic history. As our journey through Laniakea approaches its conclusion, a final realization comes into focus. Understanding our supercluster is ultimately a way of understanding ourselves. We began on a single planet orbiting an unremarkable star, unaware of the vast currents that shaped our existence. Yet step by step, map by map, we expanded our vision until the true scale of our home emerged. Not a galaxy, not a cluster, but a gravitational realm spanning hundreds of millions of light years. Laniakea ties together the stories of countless galaxies, and within that tapestry, the Milky Way is only one luminous thread. But by tracing that thread outward, we discovered a structure so immense that it reshaped our sense of identity. We are not passengers lost in an indifferent universe. We are participants in a grand motion carried through a cosmic landscape older than any star we see. To know Laniakea is to place ourselves within that vast continuum, to recognize that our lives, our history and our future unfold inside a supercluster that has guided our path since the beginning. And in that recognition, the universe becomes not just larger, but more meaningful. Standing at this point in our story, one truth becomes unmistakable. Laniakea is not merely a structure we inhabit, but a perspective that elevates everything we know. It teaches us to see the universe not as a scattered collection of stars, but as an interconnected system shaped by motion, gravity, and time. It reminds us that the forces guiding entire superclusters are the same forces that shaped the Earth and the lives that arose upon it. and it shows us that our search for meaning is inseparable from our search for understanding. The more clearly we see the supercluster around us, the more clearly we see the fragile brilliance of our own existence within it. Laniakea offers a sense of unity not through proximity but through shared motion, shared origin, and shared destiny. In recognizing this, we discover a kind of cosmic belonging that transcends borders, planets, and even galaxies. We may be small, but we are woven into a pattern vast enough to hold every world and every star we will ever know. And from that vantage point, a simple truth emerges: the universe is not something outside of us. It is the environment in which our story has always unfolded. As we near the end of this journey, the vastness of Laniakea brings us to a quiet, profound insight. Our place in the universe is defined not by size but by connection. The supercluster does not make us insignificant. It gives our existence context, a cosmic landscape through which our galaxy has been travelling for billions of years. Everything we are, from the atoms in our cells to the orbit of our sun, has been shaped by the same gravitational architecture that binds hundreds of thousands of galaxies together. And in realizing this, we uncover a deeper truth. The universe is not a void to be feared, but a structure to be understood. Its immensity is not a wall, but an invitation urging us to look farther, think deeper, and recognize the continuity between our small world and the grand motions that surround it. Laniakea shows us that meaning does not come from being central or dominant, but from belonging to a story far larger than ourselves. In that story, we are both observers and participants carried through the cosmos by forces that began long before we existed. And through understanding, we make this vast ancient home feel closer, warmer, and unmistakably ours. At this point, Laniakea becomes more than a scientific concept. It becomes a lens through which we understand the universe's deepest truth. Everything is part of something larger, from stars woven into galaxies to galaxies flowing along filaments to superclusters drifting across the cosmic web. The universe is a hierarchy of connection. And within that grand structure, consciousness emerges fragile, temporary, yet capable of recognizing the pattern that holds it. Humanity's ability to map Laniakea is a testament to this spark of awareness. We are small, yet we perceive the shape of the supercluster carrying us through space. We are brief, yet we uncover processes billions of years in motion. We are local, yet we understand structures spanning hundreds of millions of light years. This capacity to comprehend scale is one of the rarest phenomena the universe has produced, and as we reflect on it, Laniakea ceases to feel distant. It becomes the framework of our story, the vast envelope within which our history, our science, and our future unfold. In knowing it, we learn something essential. Awareness may be tiny, but its reach is vast. As our journey draws toward its final moments, a striking realization settles over everything we have explored. Laniakea is both a destination and a beginning. It is the vast structure that shaped our past, the gravitational valley guiding our present, and the cosmic landscape through which our future will unfold. Yet in understanding it, we uncover something even more remarkable: the power of awareness to bridge the smallest life with the largest structures in existence. A fragile species on a tiny world has learned to trace the paths of galaxies, to see the invisible skeleton of dark matter, and to recognize the flows that bind a supercluster into a single, unified whole. This connection is not symbolic, it is real. Our atoms were forged in stars whose motions were shaped by Laniakea's contours. Our galaxy's trajectory is written into its gravitational slopes. And our curiosity, rising from a speck of life on one planet, now spans the width of this immense supercluster. In discovering Laniakea, we've discovered the true scale of our home and the astonishing fact that we are capable of understanding it. That alone transforms the cosmos from something distant into something deeply, intimately ours. Now, at the end of this long arc through Laniakea, the pieces fall into place. We began with a question about our true home in the universe, and we discovered that home is far larger, older, and more interconnected than anything we once imagined. Laniakea is not just where the Milky Way resides, it is the gravitational realm that shaped every step of our cosmic journey. Its currents carried our galaxy before our sun existed, and they will carry it long after the last stars fade. Yet the most extraordinary discovery is not the scale of the supercluster, but the simple fact that we can understand it at all. In a universe where galaxies drift for billions of years without witnesses, awareness emerged on a single world and learned to read the structure of an entire supercluster. That act of comprehension binds us to the cosmos more deeply than gravity ever could. It turns the overwhelming into the knowable, the distant into the familiar, the immense into something we can call home. And as we close this journey, one truth remains: Laniakea will continue carrying us through the universe, but through understanding we now carry Laniakea within us. Before the first galaxies took shape, before light truly filled the universe, something else may have emerged in the dark. When the cosmos was still less than 1 billion years old, some of the most powerful objects we know already existed: black holes, with masses millions, even billions of times that of the Sun. Their presence is a mystery. How could such giants form so early, when the universe itself was still taking its first breaths? If stars were the builders of the cosmos, then these black holes were its ancient kings. They lurked at the centres of young galaxies, feeding on gas-bending light and shaping their surroundings with invisible hands. Today we can still see their distant glow, not directly but through the quasars they power. These ancient monsters are not just astronomical curiosities, they are windows into the universe's first moments, into physics pushed to its limit. And to understand them, we must follow the story back to where everything began. In the darkness after the Big Bang, the early universe was not a place of quiet creation. It was a landscape of rapid change, expanding, cooling, and assembling its first structures. Hydrogen and helium dominated everything. There were no planets, no galaxies as we know them, and no heavy elements to shape complexity. And yet, hidden in that darkness, the seeds of the cosmos were being sown. The first stars were forming. Gravity was beginning to carve matter into islands of light. But gravity doesn't just build stars, it also builds monsters. The same forces that created the first bright points in the night could also drive matter inward, crushing it into invisible singularities. These early black holes would grow fast, too fast for our current models to explain. They should not have had enough time. And yet their light from billions of years ago reaches us today, blazing like beacons through the fog of cosmic dawn. To understand these ancient giants, we need to return to the first few 100 million years of cosmic history, an era astronomers call the Cosmic Dawn. The universe was still young, barely emerging from the darkness that followed the Big Bang. Matter had begun to clump under gravity, forming the earlier stars and galaxies. But scattered among these young structures were strange, brilliant beacons, quasars powered by black holes far too massive for their age. These quasars shine so brightly that they can outglow entire galaxies, making them visible across the cosmos. They are powered by black holes devouring matter at extraordinary rates. The puzzle is simple but profound. How could black holes grow so huge in so little time? Either our understanding of their formation is incomplete, or the early universe had pathways we've never fully grasped. This is the mystery scientists now chase across billions of years of light. The first clues came from the faint light of distant quasars. Astronomers found them shining from a time when the universe was less than 1 billion years old. Their brightness told a shocking story. At their cores were black holes already weighing hundreds of millions of suns. These objects didn't just exist. They thrived. They consumed matter faster than any known mechanism should allow, and their very presence meant something fundamental in our understanding was missing. Each quasar is like a time capsule preserving the state of the universe in its earliest chapters, and through these beacons we can trace the growth of black holes across cosmic history. But the numbers don't add up. Growing a black hole to such mass under known physical limits should have taken longer than the universe had been alive at that point. This is the paradox one that forces us to question everything about how black holes are born. Among the most striking examples are quasars detected at redshifts greater than 7. Their light began its journey when the cosmos was still in its infancy. Observations reveal black holes with masses of nearly 1 billion suns already fully formed. These are not quiet objects. They blaze so powerfully that they pierce through the dense fog of the early universe. Their light has travelled for more than 13 billion years, carrying the signature of a time when galaxies were just beginning to form. What's even more unsettling is how common they seem to be. If these early monsters were rare accidents, we might dismiss them as cosmic flukes, but they appear again and again in deep sky surveys. Their abundance suggests a process not just possible, but efficient. Something in the early universe allowed black holes to grow fast, perhaps even faster than we believed nature would permit. This is no isolated mystery. It's a pattern written across the cosmos. This mystery has transformed from a curiosity into a full-blown problem for cosmology. If these black holes truly existed so early, they must have formed and grown under conditions unlike anything we see today. Our current models, based on slow accretion and steady stellar evolution, simply can't keep up with the clock. It's as if these objects skipped the line of cosmic evolution, leaping ahead while the rest of the universe was still getting started. That gap between what we observe and what our models allow is at the heart of the puzzle. Somewhere between the birth of the first stars and the rise of the first quasars, something extraordinary happened. And to solve it, we must go back to the beginning, to the chaotic first, hundreds of millions of years where matter flowed freely. Gravity reigned supreme, and black holes may have found a shortcut to grow. The timeline makes the problem clearer. The first stars are thought to have ignited roughly a few 100 million years after the Big Bang. Yet by the time the universe was less than 1 billion years old, some black holes had already reached enormous masses. This gives them only a few 100 million years to form, grow and light up the cosmos as quasars. But under normal physics, that's barely enough time to build a small galaxy, let alone a billion solar mass black hole. The speed required is staggering. These black holes must have grown at rates near or even beyond the theoretical Eddington limit, the balance point where radiation pressure should push back against in falling matter. For them to exist, something must have bent or bypassed those limits. Either their seeds were born massive, or the early universe offered growth channels that we have yet to fully understand. This is why astronomers call these objects cosmic monsters. Their existence isn't just impressive, it's disruptive. They don't fit neatly into the story we've built about how the universe grows. Instead, they force us to redraw the early chapters entirely. If black holes can grow this fast, then either we've underestimated the power of gravity, or we've missed key physical processes that existed only in the young cosmos. Every theory about the early universe must now account for these ancient giants, and that's why they've become one of the most important clues to understanding cosmic dawn. To solve the paradox, we must hunt for their origins. Were these black holes born from stars? Did they collapse directly from gas? Or did some of them come from an even stranger, more primordial source, one that predates galaxies themselves? To trace the origin of these ancient giants, we must begin with the concept of black hole seeds. Every supermassive black hole started as something smaller, a seed that grew over cosmic time. But these early quasars didn't have the luxury of billions of years. Their seeds must have been massive, or their growth unnaturally fast. Astronomers are now piecing together 3 major pathways. The first involves the death of the earliest stars, enormous metal-free suns collapsing into black holes, only a few dozen to a few 100 times the mass of our Sun. If they could accrete matter fast enough, these stellar remnants might grow into the giants we see. The second path suggests something more dramatic: direct collapse. Under the right conditions, massive gas clouds could skip star formation altogether and plunge inward to form black holes thousands of times heavier right from birth. The third and boldest points to primordial black holes forged in the chaos of the Big Bang itself. If they exist, they could be older than galaxies, older than stars, older than light itself. Each of these scenarios leads to a very different cosmic story. And to find the truth, we must explore them one by one. The simplest and most traditional idea is that the first black holes were born from the death of the universe's earliest stars. These were not ordinary stars. They were colossal, hundreds of times the mass of the Sun, and burned through their fuel in only a few million years. When they died, they collapsed into black holes, leaving behind compact seeds scattered across the young cosmos. These population 3 stars, forged from pure hydrogen and helium, were the first sources of light. Their deaths would have planted the earliest black holes into the dark fabric of the forming universe. From there, the seeds could have grown by pulling in gas dust and even merging with each other. This scenario is elegant because it doesn't require any new physics. It uses processes we already understand: star formation, stellar collapse, and accretion. But it also carries a problem: time. Starting from these small seeds, even under ideal conditions, might not be enough to explain billion solar mass black holes forming so early. Something more may have been needed to accelerate their growth. The problem with stellar remnants is scale. Even the most massive population 3 stars can only collapse into black holes a few hundred solar masses at most. To grow from there to a billion solar mass monster in less than a billion years would require uninterrupted near-perfect feeding. The black hole would need to accrete matter at or above the Eddington limit almost continuously. But the universe is not so cooperative. Star-forming regions are chaotic. Feedback from radiation and supernovae pushes gas away, starving young black holes of fuel. Even under optimistic conditions, this steady growth would fall short. The math simply doesn't add up. This doesn't mean stellar remnants didn't play a role. They may have been the first seeds, the foundation. But on their own, they can't explain the sheer scale of the black holes we observe so early. Something else must have accelerated the process. Something far more efficient than ordinary stellar death. This is why astronomers began exploring a more extreme possibility. What if some black holes were born big? Instead of starting from the death of stars, they might have formed directly from the collapse of vast pristine gas clouds in the early universe. This is known as the direct collapse black hole scenario. In these rare regions, intense radiation from nearby star-forming halos could have suppressed normal star formation, allowing the gas to remain hot and stable. Without breaking up into stars, the entire cloud could collapse under its own gravity, forming a single massive black hole seed, potentially tens of thousands of solar masses right from the start. If these seeds existed, they would have had a tremendous head start. They wouldn't need hundreds of millions of years to grow to quasar size. They'd already begin the race halfway to the finish line, feeding on surrounding gas to reach their enormous masses with ease. The direct collapse model has a powerful appeal because it solves the timeline problem elegantly. A seed of 10,000 solar masses doesn't need miraculous feeding rates to become a billion solar mass black hole within a few 100 million years. It just needs steady access to gas, something the dense early universe had in abundance. But forming such a seed requires special conditions. The gas must be metal-free, hot enough to resist fragmenting into stars, and shielded from external cooling. These circumstances may have existed only in specific regions, making direct collapse a rare event. Yet rarity might be enough. Even if only a small fraction of early halos experienced these conditions, it could explain the number of quasars we observe at high redshifts. In this view, the first black holes weren't built slowly, they were born ready to dominate. The third and boldest idea reaches all the way back to the Big Bang itself. Some scientists propose that primordial black holes may have formed not from stars or collapsing gas, but from violent fluctuations in density during the universe's first moments. These would be objects born before galaxies, ancient relics of the universe's creation. If certain regions of space were just slightly denser than others, gravity could have crushed them directly into black holes. Unlike stellar remnants or direct collapse seeds, primordial black holes could have existed mere seconds after time began. If even a small population of them survived, they could have served as ready-made seeds for the supermassive black holes we see today. And if this idea proves true, it would mean these cosmic giants didn't just shape the universe, they were part of its birth. Each of these three pathways paints a very different picture of the early universe. Stellar remnants suggest a cosmos that builds slowly small seeds growing through persistence. Direct collapse implies a universe capable of taking shortcuts, creating massive black holes in a single catastrophic event. Primordial black holes push the mystery even deeper, tying their existence to the very beginning of space and time. It's possible that more than one of these pathways happened at once. The early universe was messy, chaotic, and full of extremes. Different regions may have followed different evolutionary tracks, producing a diverse population of black hole seeds. The real challenge is to find out which of these mechanisms or which combinations shaped the monsters we observe at the cosmic dawn. That means studying not just black holes themselves, but the environments that gave birth to them. Understanding how these black holes grew so fast means confronting the ultimate constraint, the Eddington limit. This limit defines how quickly a black hole can accrete matter before the outward pressure of radiation balances the inward pull of gravity. Under this rule, growth is steady but slow. Reaching 1 billion solar masses in a few 100 million years should be nearly impossible. Yet the quasars tell us it happened. Either these black holes started out far more massive than we thought, or they somehow broke the Eddington rules. Some theories suggest super-Eddington accretion, where black holes briefly feed at rates above the classical limit, driven by dense gas flows or chaotic inflows that trap radiation. If this occurred in the early universe, it could give even small seeds a fighting chance to grow into the giants we observe today. And it might mean the laws we treat as rigid were in those early moments far more flexible. Super-Eddington accretion isn't just a theoretical loophole, it may be a natural feature of the chaotic early cosmos. In dense gas-rich environments, infalling material can form thick accretion flows that trap radiation, instead of letting it push matter away. This allows black holes to gorge themselves far beyond the classical limit, growing at astonishing speeds. Some models suggest that if this feeding persisted even for short bursts, it would dramatically accelerate mass growth. A black hole could gain orders of magnitude in size over a relatively brief period. If early black hole seeds were embedded in such environments, super-Eddington episodes could have acted like cosmic rocket boosters, turning modest seeds into giants long before the universe was 1 billion years old. It's a process fast enough to match the timeline and wild enough to fit the early universe. But feeding isn't the only path to rapid growth. Black holes can also grow through mergers, the violent coalescence of two or more smaller black holes into one larger object. In the crowded early universe, galaxies were forming close together, colliding and merging in rapid succession. Their central black holes would likely have followed the same pattern. Every merger adds mass and, in some cases, momentum. A handful of well-timed collisions between early seeds could quickly build up the enormous masses we see in ancient quasars. This scenario becomes even more compelling when combined with super-Eddington feeding. Seeds formed from stars or direct collapse could merge and feed in overlapping bursts, compounding their growth. What might take billions of years today could have happened in mere hundreds of millions back then. Mergers also leave a distinct mark on the universe. When black holes collide, they unleash powerful ripples in space-time gravitational waves. These signals are faint today, but they carry the fingerprints of the first massive black holes. Detecting such waves from the cosmic dawn could reveal not just how fast these giants grew, but also how many collisions it took to make them. Future observatories like Laser Interferometer Space Antenna LISA are designed to listen for precisely this kind of signal. If LISA detects low-frequency gravitational waves from the early universe, it could confirm that mergers were a key accelerator of black hole growth. This would mean the story of the first black holes wasn't just about feeding. It was about cosmic collisions echoing through space-time. The early universe provided the perfect environment for both feeding and merging. Gas was dense, galaxies were close, and gravitational wells were deep. Black holes didn't need to search for fuel, they were immersed in it. Streams of primordial gas flowed along the filaments of the cosmic web, funneled straight into young galaxies where seeds lay waiting. These cold gas inflows could sustain black holes at extreme accretion rates for long periods. Unlike today, where galaxies are isolated and starved of fresh material, the early cosmos offered a constant supply line. This cosmic buffet may have been the key to unlocking explosive growth. With abundant fuel and frequent mergers, even modest seeds could transform into billion solar mass giants, just in time to light up the universe as quasars. But even with these mechanisms, something still feels extraordinary. To produce so many massive black holes so quickly, these processes must have been not just possible but common. That means the early universe may have been far more efficient at making black holes than we once imagined. Star clusters may have formed in runaway bursts. Gas inflows may have persisted longer than expected. Mergers may have happened at breathtaking frequency. What today would be considered rare, even exotic, might have been the normal state of the cosmos back then. If this is true, then these black holes didn't just appear early. They were part of the natural rhythm of the young universe, shaping it as much as it shaped them. The impact of these early giants reached far beyond their immediate surroundings. As they fed and merged, they released powerful jets and intense radiation that pierced through the fog of the early cosmos. This energy didn't simply vanish, it transformed the universe. These black holes heated and ionized the gas around them, helping to clear away the cosmic mist left after the Big Bang. They turned dark regions into glowing pockets of light, pushing the universe toward a new era. In this way, the first black holes were more than passive objects. They were engines of cosmic change, shaping their environment on a scale rivaling galaxies themselves. Their rise and the rise of structure in the universe were deeply intertwined. This era is known as cosmic reionization, the moment when light from the first stars, galaxies, and black holes reionized the hydrogen fog filling the universe. For a long time, scientists believed stars were the main drivers of this transformation, but evidence increasingly suggests black holes may have played a far larger role than expected. Their radiation is harder, more penetrating, capable of carving ionized bubbles that spread quickly through the intergalactic medium. A relatively small number of actively feeding black holes could have accelerated reionization dramatically. If this is correct, then the first black holes didn't just grow within the universe, they helped shape the very conditions that allowed it to become transparent and visible. This creates a powerful feedback loop. As black holes grow, they emit energy that clears gas from their surroundings, altering how galaxies evolve. In some cases, this may choke off further growth by pushing fuel away. But in the chaotic early universe, it may have done the opposite, opening new channels for fresh gas to flow in along the filaments of the cosmic web. This positive feedback could create a runaway effect. The more a black hole fed, the more it shaped its environment to feed even more. Instead of being isolated engines, these early giants may have worked in concert with their galaxies, accelerating their mutual growth. This synergy may be why early quasars appeared so suddenly, not as rare outliers, but as products of a cosmic system tuned for rapid growth. If black holes truly helped reionize the universe and shape its structure, then they weren't just passengers in cosmic history, they were architects. Their rise marks a turning point, the universe transitioning from darkness to light, from diffuse gas to structured galaxies. Their radiation and gravitational pull likely influenced where stars formed, how galaxies clustered, and how matter flowed along large-scale filaments. What we call the cosmic web may in part have been sculpted by their presence. This also means that understanding the first black holes isn't just about understanding quasars, it's about uncovering the engine behind the transformation of the entire universe, a force that shaped everything that followed. The fingerprints of this transformation are still written across the sky today. Astronomers can see them not in visible light, but in the faint background glow left behind by ancient hydrogen. a subtle signal from the epoch of reionization. The timing and strength of this signal carry clues about how powerful the first black holes really were. If they grew and fed as rapidly as current observations suggest, their influence should be detectable in the structure of the intergalactic medium itself. In other words, by reading the sky carefully, we can reconstruct their rise. And as technology advances, those faint whispers from cosmic dawn are slowly becoming clear voices. The James Webb Space Telescope has already pushed our view deeper into the early universe than ever before, revealing young galaxies that existed just a few 100 million years after the Big Bang. Among them, astronomers are finding hints of unusually bright, compact sources that may signal the presence of growing black holes. These are not the massive quasars we detect from billions of light years away. They are smaller, quieter seeds in the making. Observing them gives us a rare glimpse of black holes, not in their prime, but in their infancy. Every data point helps refine the story, bringing us closer to understanding how the universe managed to create such monsters so quickly. Future observatories promise to push even deeper. Missions like Laser Interferometer Space Antenna will listen for gravitational waves from merging black holes in the early universe, while next-generation telescopes will hunt for faint signals from the smallest seeds. By combining these tools, scientists can reconstruct how black holes grew from invisible whispers to cosmic engines. This is more than an astronomical quest. These observations may reveal which formation pathways dominated, how often mergers occurred, and how quickly accretion proceeded. They may even hint at whether primordial black holes truly existed. For the first time, we are approaching an era where these mysteries can be tested, not just imagined. These upcoming observations won't just refine our models, they'll rewrite them. By comparing light gravitational waves and the structure of the intergalactic medium, scientists can piece together when and how the first black holes formed. This multi-messenger approach will let us trace their evolution in ways that were impossible just a decade ago. It will also allow us to separate the fingerprints of different formation pathways. A universe dominated by stellar remnants would leave a different signal from one shaped by direct collapse or primordial origins. The more precisely we can measure these signatures, the closer we come to uncovering the true story of the first giants, and by extension, the forces that shaped everything that followed. But even as technology advances, one truth remains. These black holes formed in a universe unlike anything we know today. It was hotter, denser, and far more dynamic. Star formation ignited in a flash, galaxies assembled at breakneck speed, and gas flowed through the cosmic web like rivers. In such a setting, growth that seems impossible now may have been almost inevitable then. What looks like a paradox to us may have been the natural pace of creation at cosmic dawn. The question is not only how the first black holes grew, but why the young universe was so efficient at feeding them. The answer to that question may reshape our understanding of structure formation itself. The first black holes are more than relics of a distant past. They are keys to understanding how the cosmos built itself. Their rapid rise hints that the universe may have been primed for black hole growth from the very beginning. These objects didn't just emerge alongside galaxies. In many cases, they may have led the way, anchoring the centers of young proto-galaxies and driving their evolution through gravity and feedback. Instead of being passengers, they may have been the architects around which galaxies took shape. This flips the traditional view on its head. Perhaps galaxies didn't build black holes. Perhaps black holes helped build galaxies. This idea isn't just speculation, it's supported by what we see in the modern universe. Nearly every massive galaxy hosts a supermassive black hole at its center, and their masses are tightly correlated. This relationship hints at a co-evolution that may have begun at the very dawn of time. If black holes grew rapidly first, they could have acted as gravitational anchors pulling in gas and stars accelerating galaxy formation. Over billions of years, this bond between black holes and their host galaxies shaped the cosmic structures we observe today. In that sense, the rise of the first black holes may not have been a side effect of cosmic evolution. It may have started it. If this is true, then the search for the earliest black holes is also the search for the origin of galaxies themselves. Every early quasar we find isn't just a point of light from the past, it's a blueprint of how cosmic structure assembled. By studying their environments, we can learn how gas collapsed, how stars formed, and how gravity shaped the young universe. Their intense energy output likely regulated star formation, controlling how galaxies grew around them. The ancient black holes are not just astronomical objects, they are narrative threads woven into the very fabric of cosmic history, holding the timeline of galaxies and light together. This perspective transforms black holes from endpoints of stellar death into engines of creation. They may have set the pace of structure formation, dictated how galaxies matured, and ignited some of the first major feedback cycles in the cosmos. It also means their origins are tied not only to extreme physics, but to the architecture of the universe itself. To truly understand where we come from, we must understand how these cosmic anchors appeared so early, so massive and so influential. Their story is in many ways the story of everything else that followed. As we peel back these layers of cosmic history, a larger picture emerges. The first black holes were not isolated accidents of physics. They were structural pillars of the young universe. Their gravity-anchored galaxies, their radiation reshaped space, their mergers echoed through time. Every observation we make of them is like finding a fossil, except these fossils are made of light and space-time itself. By studying them, we're not just learning how black holes formed, we're uncovering how the entire cosmic landscape was built. Their story began in darkness, but their influence still reaches us today, written across the stars, galaxies, and filaments of the universe. The deeper we explore the universe's first billion years, the more black holes reveal themselves not as silent observers, but as active architects. Their gravity sculpted galaxies, their energy reshaped the intergalactic medium, and their growth left imprints that we are only now learning to decode. This isn't just about understanding a few extraordinary objects. It's about uncovering the hidden framework beneath cosmic history, the forces that determined how light, matter, and structure emerged from darkness. And with every new observation, the timeline of black hole formation becomes sharper, more intricate, and more astonishing than anyone expected. What makes this story extraordinary is that it isn't over. These black holes may be ancient, but they continue to shape the cosmos today. Every galaxy with a supermassive black hole at its heart carries the legacy of those early seeds. Their formation wasn't a distant, isolated event. It was the opening act of a drama still unfolding. The gravitational ripples from their collisions still travel through space. Their influence can be seen in the way galaxies cluster, spin, and evolve. In this sense, the first black holes didn't just belong to the past, they built the universe we inhabit. To understand them is to understand our cosmic foundation. The rise of the first black holes is more than a scientific mystery. It's a turning point in cosmic history. It connects the moment the universe emerged from darkness to the structures we see today. It links the faint light of cosmic dawn to the vast web of galaxies stretching across space. Their story bridges two eras, one ruled by gas and gravity and another shaped by galaxies and stars. Without these early giants, the timeline of the universe would unfold very differently. In many ways, they were the silent architects of everything that came after. The mystery of the first black holes began with a paradox: how they could exist so early. But now that paradox has become a map. By tracing their growth, their impact on reionization, their role in galaxy formation, and their fingerprints in gravitational waves, we are uncovering the structure of the young cosmos itself. Their story ties together nearly every major process in the first billion years: star formation, mergers, radiation feedback, cosmic web flows, and the birth of galaxies. What once seemed like isolated beacons of light are now recognized as central players in the unfolding of the universe. And yet every answer reveals deeper questions, pulling us further toward the origin of it all. Somewhere beyond the distant quasars, beyond the galaxies, we can currently see lie the very first black holes, silent, invisible, and ancient. They are too faint for even our most powerful telescopes to detect directly, but their influence is everywhere, hidden in the structure of the cosmic web, in the ionization of the early universe, and in the seeds of the galaxies that followed. Finding them isn't just a matter of sharper eyes, it's about learning to read the universe's earlier signatures. These signals are subtle, but they're written into the fabric of space itself, waiting for us to uncover them. And when we finally do, the story of the universe's beginning may change forever. This is the next frontier of cosmology. Not just seeing light, but hearing the echoes of darkness. Gravitational waves, faint hydrogen signals, and indirect patterns will reveal what light alone cannot. Instruments like laser interferometer, space antenna, and future radio arrays will allow us to peer behind the veil of cosmic dawn. They're in that silent era the first black holes were born. They left no light, only their gravitational fingerprints. And with every new generation of instruments, our ability to detect those fingerprints grows stronger. The hunt has already begun. Each step closer to detecting these earliest black holes isn't just about pushing technology. It's about pushing the limits of what we can know about the beginning of everything. Their formation holds clues about gravity, matter, and even the physics that shaped the universe's first seconds. They are bridges between the quantum chaos of the early cosmos and the structured universe we see today. Studying them could reveal not just how galaxies formed, but whether there are deeper laws of nature we've yet to uncover. The first black holes may be ancient, but their echoes may rewrite our understanding of the cosmos itself. The coming decades will be a golden age for this hunt. Gravitational wave detectors, advanced radio telescopes, and deep infrared observatories will give us the power to trace the first black holes, not through their light, but through their impact on the universe itself. Each new signal, a ripple in space-time, a faint radio whisper, a distorted glow from a young galaxy will bring us closer to these invisible giants. The earliest black holes may have been born in silence, but their presence was anything but quiet. The cosmos still carries their fingerprints, waiting for us to uncover them piece by piece. The hunt for the first black holes is not just a search for ancient objects, it's a search for the moment the universe changed. Their birth marked the beginning of a new cosmic era, galaxies assembling around dark cores, light piercing the fog and structure taking shape on the larger scales. The clues are all around us in gravitational waves, faint radiation, and the architecture of the cosmic web itself. Each discovery tightens the timeline, refines the models, and brings us closer to the dark origins of these giants. And somewhere ahead, the universe's oldest black holes are still waiting silent, but not lost. When we finally detect these earliest black holes directly, it will be more than a scientific milestone. It will be like turning the first page of the universe's unwritten history. For decades, we've known them only through their echoes, the distant light and the scars they left on space-time. Soon we may be able to see their birth not as distant myths, but as real measurable events. Their discovery will not close a chapter, it will open one. It will reveal how darkness itself shaped the universe, and how the first cosmic giants carved the path for everything that followed. And when we arrive there, the story of the universe will begin not with light, but with shadow. To push beyond what we know, astronomers are designing precision tests to catch the earliest black holes in the act of forming. One of the most promising tools is laser interferometer space antenna, which will be sensitive to low-frequency gravitational waves produced when massive black holes merge at high redshifts. Detecting such a signal would be like listening to the heartbeat of the early universe. It would reveal not only how massive these black holes were, but how often they collided, giving us direct insight into their growth channels. Unlike light, gravitational waves carry information untouched by dust or time, perfect messengers from cosmic dawn. Alongside gravitational wave astronomy, the James Webb Space Telescope will continue to probe the faintest galaxies and quasars at extreme redshifts. Its infrared sensitivity allows astronomers to detect the earliest accretion disks, the glowing regions around young black holes as they feed. By measuring their luminosity and spectral signatures, scientists can estimate black hole masses and growth rates with unprecedented precision. If Webb detects black holes already massive just a few 100 million years after the Big Bang, it would strongly favour direct collapse or primordial scenarios. Every faint distant light source it captures is potentially a seed black hole in its first breaths of cosmic life. Radio astronomy is another powerful key. Instruments like the upcoming Square Kilometre Array will map the faint 21 centimetre hydrogen line, revealing how early black holes influenced their surroundings. As these objects heated and ionized nearby gas, they left measurable signatures in this background signal. By studying subtle fluctuations in the 21 centimetre spectrum, astronomers can reconstruct where and when black holes formed, even if they are too faint to observe directly. This allows us to probe their environment as well as their existence. It's like seeing the shadow of a giant before ever glimpsing its face. Combining gravitational wave data, infrared observations, and 21 centimetre mapping creates a multi-messenger picture of early black holes. Each method reveals a different aspect: mergers, accretion rates, environmental influence. Together, they allow scientists to test formation models rigorously. For example, if mergers dominate, gravitational waves will be abundant at high redshift. If direct collapse seeds are common, infrared signatures of massive early accretion disks will appear. Primordial black holes would leave a subtly different imprint detectable indirectly through the distribution of matter and early galaxy formation patterns. This integrated approach is essential to unraveling one of the deepest mysteries of cosmic dawn. All of these observations aim to answer a single fundamental question: how did the first black holes grow so quickly? Were they born massive, or did they feed and merge in extreme conditions? Did primordial physics play a role we've yet to uncover? By combining multiple observational channels and theoretical models, astronomers are beginning to constrain the possibilities. Each new quasar, each gravitational wave detection, each faint infrared signal adds another piece to the puzzle. Ultimately, solving this mystery will reveal not just the origin of black holes, but the processes that shape the universe's earlier structures, the foundations of galaxies, stars, and light itself. The study of the first black holes also informs our understanding of galaxy formation. Massive early black holes likely influenced the dynamics of surrounding gas, regulating star formation through feedback mechanisms. Their energy output could heat or expel gas, shaping the structure and evolution of young galaxies. This relationship may explain why supermassive black holes and their host galaxies display tight correlations in mass and activity today. By examining the earliest examples, scientists hope to trace the co-evolution of black holes and galaxies back to cosmic dawn. In this sense, the first black holes are both products and architects of the universe's formative years. Feedback from the first black holes was not uniform. Some galaxies experienced intense radiation and outflows that suppressed star formation locally, while others may have funneled gas efficiently toward the black hole, accelerating growth. Simulations suggest that these variations helped create the diversity of galaxy types observed today. Elliptical galaxies, spiral galaxies, and massive clusters may all carry imprints of early black hole activity. By connecting black hole feedback to galaxy morphology, astronomers are beginning to see the first black holes not only as relics, but as dynamic agents that shape the architecture of the universe itself. Mergers between early black holes also played a key role. In a universe where galaxies were closer together, collisions were frequent. When two black holes merged, they combined, their mass grew faster, and sent gravitational waves rippling across space-time. These mergers could create some of the earliest supermassive black holes, explaining their surprising masses at high redshift. The signals of these events are now targets for next-generation detectors like laser interferometer space antenna. By detecting these ripples, astronomers can reconstruct a timeline of early mergers, providing insight into how black holes coalesced and shaped the young universe. Cold gas inflows along the cosmic web provided another crucial channel for growth. Streams of pristine hydrogen and helium could funnel directly into young galaxies, feeding black holes at high rates without interruption. These cold flows create environments where black holes can sustain near-constant accretion, bypassing the limitations of intermittent stellar feeding. Combined with mergers and super-Eddington accretion, cold gas inflows make rapid growth plausible even in the universe's first few 100 million years. This mechanism links large-scale structure directly to black hole evolution, showing how the universe's scaffolding supported its earliest monsters. Primordial black holes remain the most speculative pathway. If density fluctuations in the immediate aftermath of the Big Bang were extreme enough, regions of space could have collapsed directly into black holes seconds after the universe began. While direct evidence is lacking, their existence would explain how some supermassive black holes appeared too early for stellar or direct collapse seeds to account for. Primordial black holes could have served as universal seeds silently waiting in the cosmic darkness, shaping the formation of galaxies and the earliest quasars before stars had even formed. The combination of these pathways, stellar remnants, direct collapse, primordial formation, suggests a universe rich with black hole seeds. Some were small and grew through accretion, others were massive from birth, and a few may even predate galaxies entirely. This diversity provides a natural explanation for the variety of quasars and supermassive black holes observed at high redshift. It also implies that the early universe was an environment where extreme physics was the norm rather than the exception. Understanding the balance between these mechanisms remains one of the most compelling challenges in modern cosmology. Observations and simulations now work hand in hand. High-resolution cosmological simulations track how gas dark matter and black holes interact, predicting how early seeds might grow under realistic conditions. Comparing these predictions to observations from James Webb Space Telescope allows astronomers to rule out implausible scenarios and refine models. Each newly discovered high-redshift quasar provides a data point to validate or challenge theories of black hole formation. This iterative process is crucial for understanding how the first black holes shaped the cosmic landscape we observe today. The early universe's density and temperature played a critical role in black hole growth. Dense gas clouds funneled matter efficiently into potential wells, while higher background temperatures influenced cooling rates and star formation. These environmental factors, combined with mergers and accretion, could explain how black holes reached extraordinary masses so quickly. Understanding these conditions helps astronomers identify where to look for the youngest and most massive seeds. By linking cosmic conditions to black hole evolution, we begin to see a coherent picture of how the universe built its first gravitational titans. Studying the environments of early black holes also sheds light on the first galaxies. Gas inflows, radiation feedback, and mergers all influence both black hole growth and star formation within the same regions. This interplay created a feedback loop. As black holes grew, they shaped galaxy evolution. As galaxies formed, they provided fuel for further growth. Observing these early systems allows scientists to connect the dots between black hole formation and the assembly of the first luminous structures in the cosmos. In essence, the rise of the first black holes is inseparable from the rise of galaxies themselves. The earliest black holes also inform our understanding of reionization. Their high-energy radiation contributed to ionizing hydrogen across the intergalactic medium, complementing the radiation from the first stars. By estimating the number, mass, and growth rate of these black holes, astronomers can assess how much they accelerated the universe's transition from opaque to transparent. Their contribution may have been significant, reshaping the timeline of cosmic dawn. Thus, the first black holes were not only architects of galaxies, but also agents that cleared the cosmic fog, allowing light to travel freely for the first time. Looking forward, next-generation observatories will provide unprecedented insights. Telescopes like the Extremely Large Telescope (ELT) and space-based infrared instruments will detect fainter and more distant quasars, revealing black holes closer to their formation epoch. Simultaneously, gravitational wave detectors will capture mergers of early black holes, offering a direct view of their growth via collisions. Together, these tools promise to uncover the full life cycle of the universe's first giants, allowing astronomers to test each formation pathway: stellar remnants, direct collapse, and primordial origins with real data rather than theory alone. Every discovery of a high redshift black hole adds to a growing map of the early universe. By combining observations of quasars, accretion disks, mergers, and environmental effects, scientists can reconstruct a timeline of how the first black holes formed and grew. This multi-messenger approach allows for cross-validation. Gravitational waves confirm mergers, infrared light reveals accretion, and 21-centimeter observations show the impact on surrounding hydrogen. Together, these methods provide a comprehensive view of the universe's first monsters, linking black hole formation to galaxy evolution and cosmic reionization. The data we collect today will inform simulations that attempt to recreate the early universe. By inputting observed properties of black holes' gas inflows and galaxy environments, scientists can test whether their growth can be explained by known physics, or if new mechanisms are required. These simulations also help predict where future observations should focus, guiding the search for the smallest seeds or the most massive early black holes. In this way, observation and theory work hand in hand, gradually revealing the processes that allowed the first black holes to rise so rapidly in the young cosmos. As simulations improve, they reveal subtle interactions that might have accelerated early black hole growth. For instance, dense gas flows along cosmic filaments could funnel material efficiently, while nearby star formation could generate radiation that regulates accretion rates. Mergers of black holes within close protogalactic groups may have further boosted mass growth. Each factor compounds the others, creating conditions in which black holes could reach extraordinary sizes much faster than previously predicted. Understanding these complex dynamics is essential to explaining how the universe produced its first supermassive black holes so quickly. Observations also suggest that early black holes were not solitary. Many resided in dense clusters of proto-galaxies where frequent interactions and mergers were inevitable. These crowded environments amplified growth opportunities, providing both fuel and collision partners for black holes. Such clusters could explain the apparent overabundance of massive quasars at high redshift. By studying the distribution and frequency of these objects, astronomers can estimate the typical environments where early black holes thrived. This paints a picture of the early universe as a bustling network where black holes formed, grew, and influenced everything around them in a rapid succession. Feedback from early black holes had profound consequences for their host galaxies. Radiation and outflows could regulate star formation, preventing gas from collapsing too quickly, while shaping the density and structure of the surrounding medium. In turn, these galaxies determined how much material the black holes could accrete. This mutual influence established a co-evolutionary relationship linking the growth of black holes to the assembly of galaxies. Studying this interplay at high redshift helps explain the tight correlations observed between supermassive black holes and their galaxies in the modern universe. By examining the light from distant quasars, astronomers can infer the mass spin and accretion rate of early black holes. Spectroscopy reveals the composition and velocity of surrounding gas, indicating how rapidly these objects are feeding. Combined with models of galaxy formation, this information helps constrain which formation pathways were likely. For example, extremely massive seeds observed early may favor direct collapse or primordial scenarios over stellar remnants. Each new observation sharpens the picture of how black holes became the cosmic titans we see even in the first billion years. The story of the first black holes is far from over. They are more than relics. They are foundations of the universe's structure. By tracing their origins, growth and influence, we uncover the processes that shaped galaxies' regulated star formation and even contributed to cosmic reionization. Future observations promise to reveal whether these giants were born massive, grew through extraordinary feeding, or emerged from primordial fluctuations. Each answer will not only explain the past, but also point toward new mysteries hinting at forces and events that remain hidden in the dark. The first black holes mark the beginning of a larger cosmic story, one that is only just beginning to unfold.